Everyone. In this video, we're going to go over our new chapter, which is all about conjugated pi systems and pericyclic reactions. So down below, I have a couple of examples. In the first one, we have the molecule Lycopene, and this is responsible for the color of tomatoes. And you can already see that there are a lot of double bonds or pi bonds in this molecule. And I'm actually going to highlight all of the double bonds that are separated by one sigma bond or a single bond. So if you do have alternating double bonds and single bonds, that's a conjugated pi system. Now, if you have a double bond that's further removed from another double bond, that's just an isolated double bond. So we'll talk a little bit more about these conjugated systems on the next slide. But first, I also wanted to show you the example down below of a pericyclic reaction. So this might look familiar because it is the Diels-Alder reaction. And we saw an example of this in a previous lab. Now, in the lab, we used pretty complex reactants, but for a Diels-Alder reaction, you just need something with two double bonds called a diene, and then an alkene. And the pi electrons are going to move around and create new bonds. So in this simple Diels-Alder reaction, our product is cyclohexene. So we created these new bonds here, and then we moved the double bond over. But again, we'll talk about that later on. So first, let's just focus on conjugated pi systems. So like we said on the last slide, a conjugated pi system has alternating double and single bonds. And because we have alternating double and single bonds, we can also have resonance structures. And remember, resonance can stabilize a molecule. So we'll talk a little bit more about stability later on for these pi systems. But let's just draw a few examples here. So I'm going to draw a couple of molecules, and we'll go through each one. All right, so looking at the first molecule, we have alternating double and single bonds. So we have two double bonds that are separated by one sigma bond. So that is a conjugated diene. Now, next to that, we have two double bonds that are separated by more than one single bond. So this would actually be isolated double bonds or isolated dienes. And then in the last example, we have two double bonds right next to each other. So this would be called a cumulated diene. So the conjugated diene that we have on the left only has carbon bonds, or carbon and hydrogen bonds. But we could also have other double bonds in our conjugated system. So for example, we could have a carbon-oxygen double bond, and as long as it is one single bond away from another double bond, it's also considered conjugated. And this would actually be called a conjugated enone due to the double bond and the ketone. All right, so I mentioned that conjugated systems do have resonance. If we have isolated dienes, we do not have resonance. There are just too many single bonds in the way for resonance to occur. And then in the cumulated diene, those double bonds are really close together. We could have a potential resonance structure there, but the cumulated diene isn't seen quite as often as the others. All right, so let's actually look at that conjugated enone. And let's try to figure out what the resonance structures for this molecule look like. All right, and we're only going to move one pi bond at a time for these resonance structures. So which pi bond should we move first? Well, one option is to move the pi bond between carbon and oxygen, and we'll move those electrons up to oxygen. So now we have a positive carbon and negative oxygen. So what could we move next? The other pi bond, and we could move it over so that the positive charge will be shared between the two carbons. Okay, so now our double bond has moved. And the positive charge is on that first carbon over there. Okay, so these are our three resonance structures. And notice that the single bond in the first resonance structure became a double bond in the last resonance structure. So that bond is actually not as flexible as a single bond because it has partial pi bond characteristics. So let's just make a note of that. So it's not as flexible as a single bond due to partial pi bond characteristics. Okay, so let's talk a little bit about the molecular orbitals for each of the atoms in this molecule. So I'm just going to redraw the first resonance structure. And let's go through and figure out what the hybridization of each atom is. So let's look at this carbon on the left-hand side of the molecule. What is the hybridization of that carbon? So is it sp, sp2, sp3? sp3. So it's bonded to 3 hydrogens and a carbon. So it has 4 bonds total. So that means its steric number is 4 and its hybridization is sp3. So this is from a really long time ago. So if you're feeling a little rusty, that's okay. We're here to review. Now let's move to the next carbon. Is that sp, sp2, or sp3 hybridized? So that one is sp2 hybridized. That carbon is bonded to 2 other carbons and 1 hydrogen. So its steric number is 3. So it is sp2 hybridized. And what about the one next to that? That is also sp2 hybridized. What about the next carbon over? sp2, And the last carbon, sp3. So that one looks similar to the first carbon on the left, where it's bonded to 3 hydrogens and 1 carbon. So it has a steric number of 4, so it is sp3. Now, one last question. What about oxygen? And let's draw the lone pairs on oxygen. Is that sp, sp2, or sp3 hybridized? So it has 2 lone pairs and 1 bond to the carbon down below. So that's a steric number of 3. So that is sp2 hybridized. Okay. So what does that mean for this molecule? Well, remember, when we hybridize orbitals, we combine s and p orbitals. So for the sp2 hybridized orbitals, we're combining 1s and 2p orbitals. And that will give us 3 sp2 orbitals, and then 1 2p orbital will be left over. So all of the sp2 hybridized atoms will have a p orbital that's just hanging out, and that can form pi bonds, right? All right, so let's just draw our molecule with these p orbitals that are just hanging around. So I'm going to draw the p orbitals for all of the sp3 hybridized atoms. And then the carbons on either end are sp3 hybridized, so we'll just draw the hydrogens on them, just so we know that they're different. Okay, so if we have all of these p orbitals that are lined up with each other, the electrons can delocalize, kind of similar to what we saw in the resonance structures. So the electrons can move back and forth between the 3 carbons in the oxygen that are sp2 hybridized, and this can create some stabilization along that molecule as well. All right, so again, this is all coming from first quarter of OChem, so it's okay if you feel like you haven't seen this in a while. But again, the electrons will delocalize, and that's where the partial pi bond characteristics come from for that middle bond. All right. Now, let's talk about kind of an interesting set of conjugated dienes. All right, so we have this situation where the 2 double bonds are trans to each other, so they're pointing in opposite directions. And we're actually going to call this S-trans, and the S stands for the single bond in the middle. So if we're looking at that single bond in the middle, the double bonds are facing in opposite directions, which is why it's trans. But also, what's the name of this compound? How would we name this compound? So the longest carbon chain has 4 carbons. So we would use butane, but we have 2 double bonds in this molecule, so I'm going to erase the N and the E and put diene in there. So it's butadiene. And then we have to specify where the double bonds are on the chain. So I'm going to start from the top. So that would be 1, 2, 3, and 4. So the double bonds start at carbons 1 and 3. So this is 1,3-butadiene. And I guess either way we number it, it will be the same. Okay, now we also have the cis version. So this would be the S-cis version of 1,3-butadiene. So again, we're looking at that single bond, and the double bonds are pointing in the same direction. Okay, now, any guesses on which one is more stable? So do you think S-trans is more stable, or do you think S-cis is more stable? So S-trans is more stable. But why? Why do you think S-trans is more stable than S-cis? So remember, electron groups like to be as far apart as possible from each other. So S-trans would be more stable than S-cis because those two very electron-rich double bonds are as far apart from each other as they can be. Now, it is possible to convert from one to the other, but it does take some energy. And in fact, it takes 15 kilocals per mole in order to switch from the trans configuration to the cis configuration. Now, because S-cis is less stable, it's actually more reactive. But this is something we've seen a lot of throughout organic chemistry. When something is less stable or has more energy, it can react more because it's trying to become more stable through a reaction. All right, so this is something that's going to come up later when we're talking about pericyclic reactions. So this is just something to keep in mind. Now, S-trans, because it is more stable, is 98% abundant. And S-cis is only 2% abundant. So that's how stable the trans molecule is compared to the cis molecule. All right, so now let's look at how we can create some of these dienes. So what reaction can we do in order to prepare a diene? Well, what we can do is start with an allylic halide. So an allylic halide would have a double bond and a halogen. And the halogen is in the allylic position. So remember, the allylic position is 1 carbon away from the double bond. Now we can do a simple elimination reaction to get our other double bond. So what we'll use is a bulky base in order to prevent any substitution from occurring. So we can use potassium tert butoxide, and this will go through an E2 mechanism. So remember, in elimination, we have a bulky base or a small base, depending on what elimination we're doing. And that base is going to take a hydrogen, which will leave its shared electrons behind, and then the leaving group will leave. And then we get our diene. And this one will be the S-trans diene. And again, this is 1,3-butadiene. So again, this is also the Hoffman product because we used a bulky base to produce the less substituted alkene. Now there is another way that we could make this same product. So we could start with a dihalide. So on this one we have 2 halogens and they're on separate carbons or adjacent carbons. And we're just going to use excess potassium tert butoxide. So again, this will be an E2 reaction. And the tert butoxide is going to perform 2 elimination reactions here. So it will take a hydrogen from one end, and then another tert butoxide molecule will come in, and it will take a hydrogen from the other side. And we get the same product, that S-trans product. Now, how would we form the dihalide? Do you remember how we form a dihalide? So we need an alkene. So the double bond could be in the middle there. And then we could add Br2 across the double bond. So that would be an addition reaction. All right. So we've talked about a lot of stuff that was actually covered a long time ago. We talked about molecular orbitals and resonance structures. We also talked about elimination reactions and addition reactions. So this was a lot of review, but now we're going to apply all of these concepts we've learned towards these double bonds, these pi systems. All right. So in the next lecture, we're going to talk a little bit more about molecular orbitals, and that will lead us into a discussion of the stability of these pi systems. So I will see you then.